In this course, we are going to be primarily working with digital communication. That much is clear. Now, what is not clear perhaps to me is whether you also done something about digital communication. For example, you must have done at least PCM. You not done PCM also.
Not even done pulse analog.
Analog pulse modulation schemes.
Let's clarify. I mean, what we have done in analog completely. Most of analog. Let's clarify that. Like we've done AM.
You've done all of AM and
Noise analysis and analog communication you are done completely, right? Okay, you may have your doubts for which you may want your clarifications. That's what you're saying, right? What I suggest we'll do is, as far as our formal lecturing of these 3 hours per week is concerned, let it be on new topics so that you learn new things. I'm ready, if you are ready, to devote an extra hour every week, up to an extra hour every week, if you give me a suitable time slot, wherein we'll clarify your old doubts as well as any doubts that are created in these lectures. You know, we have slightly less flexibility as far as these lectures are concerned, because we are talking in a slightly formal way. We can meet in a normal classroom in the 4th lecture and be normal selves and talk as we should. Okay? So is that okay with you? Will you be able to give me a 4th slot in which we can discuss these things nicely, whatever doubts are left? Is that okay with everybody? Thursday 1 to 2. I'll have to confirm with my timetable. I still don't know my full timetable, and I'll confirm it in the tomorrow's class. Okay. Is there any other slot available?
other groups might be having their Thursday 1 to 2 is free.
Okay. That sounds fine with me then, right? I mean, I hope it is okay with me. I'll just check. Now, maybe I can just start a little bit. I don't know, because I didn't know where to start, so I am not really prepared. Maybe I'll just tell you what kind of course outline that I can plan for you. One possible course sequence would be as follows. I'll of course start with some introduction. And since you have not done anything on PCM and delta modulation you have done?
No.
So no analog to digital conversion of any kind?
No.
At least in, sorry?
In other courses we have done analog to digital conversion.
So you know the A to D conversion technique, but you don't know in the context of communications, right? So we'll do this A to D conversion techniques. And that will include PCM and delta modulation. Of course, all of you know what PCM stands for. After discussing the basic principles of pulse code and delta modulation, we look into some of the associated problems of transmission of these kind of signals, particularly some advantages like multiplexing, time division multiplexing. You must have done frequency division multiplexing in the context of analog communication. In digital communication, we
Idea was given for how it's done over telephone.
Just the way
All right, whatever extra you think you have not done, we'll take care of in the fourth slot. Rest assured, right? We'll do that. No problem about that. But the multiplexing that we will do as part of this course is really TDM, time division multiplexing. That's what it's going to be all about. Also, concepts like line coding associated with transmission of digital information. All right. Next, we'll take up digital communication in a baseband form. Now, digital communication can be done in two ways. One is in the baseband form, the other is in a modulated form. Just like analog communication is done in a modulated form, but the digital communication can be done in both the ways, depending on the kind of channel you're working with. Whether you have a wideband channel on which baseband signals can be supported, or whether you have a radio channel in which you must first introduce the information or embed the information onto a carrier. In which case you have to do some kind of modulation again, right? But first we'll take up the question of or the techniques of baseband digital communication. All right. Now there will be a number of concepts here. I'll give you a summary of this course outline separately, but I just want to give broad titles of the things that we're going to cover. After doing baseband digital communication techniques, which involve what kind of pulse shapes to use, and concepts of intersymbol interference that arises due to band limitation on a channel, we'll see also some techniques of how to take care of such problems. We'll go into what are called digital modulation techniques. Okay. And finally, we'll spend some time on information theory and coding. That broadly covers the main topics that we'll deal with. If we do have time beyond these, I will spend some time on some other aspects of digital communication, like digital switching, which is required to connect many users to each other for talking to each other or for communicating with each other. So that takes care of modern electronic exchanges to some extent, but I'm not sure whether we will have the time to do it, but if time permits, we'll just spend some time on that, and brief overview of data networks and computer communication networks. Although we usually have elective courses of on these topics separately later on in the curriculum, so we may not cover very much of these. So that is broadly the course outline that we are going to have to deal with. Let me start by just very briefly indicating to you the advantages of digital communications. Why digital communications, right? Okay, I'll come to the book maybe next time. I have not yet decided on the final book that I should recommend to you. Now, if you look at the various communication systems that exist today in this country and abroad, we'll still find that a significant portion of these systems are still analog in nature, because of historical reasons, because most of the earliest form of communications evolved in the form of analog communication, right? But other thing that you will notice if you look at these communication systems that exist today, that they are undergoing a very fast transformation. They are rapidly being replaced by digital communication systems, very rapidly in fact. In fact, the projection is that in a decade, or maybe at the most a decade and a half from now, there will be practically hardly any analog communication systems left, except in the most, some playing some very minor role here and there. Most of the communication systems that you are going to come across in future are going to be digital communication systems. To give you an idea of how things have happened in North American continent, I don't know whether you can read this slide here. Yeah, in future I'll make the slides on these papers, but today I just had one on a plain paper, and obviously the size is not good enough, but I'll just read out to you. At least you can see the bars, right? I have broadly divided, for the purpose of this illustration, the various kinds of communication systems into 4 broad categories. These are called cable systems. That is, you communicate from one place to another place over a cable, or terrestrial microwave systems. I'm sure you're familiar with these. You must have seen microwave towers sprouting all over the countryside, which link one place to another through a microwave channel. Satellite systems, and finally fiber optic systems. I don't think one needs to, these are very common knowledge kind of things, and I'm sure all of you are quite familiar with these systems. Now, what I've shown under each of these kinds of systems is the extent of analog, the fraction of analog part and the digital part, and the way things were in 1984 and the way things were in 1990. Okay, so that shows the evolutionary trend between analog and digital. As far as cable systems are concerned, well, you will find that both the things have come down a little, because cable systems are being rapidly replaced with other kinds of systems, because laying cables are very expensive affairs and very cumbersome affairs. So cable systems in general, both in the analog and the digital form, have come down. This is the North American continent story. Coming to the terrestrial microwave, the analog part is come down quite significantly. The digital part has correspondingly gone up. Similarly for the satellite systems, and similarly for the fiber optic systems. And this trend is going to continue in the next decade or so, even there. And it's going to be much more pronounced in our country, where a lot of communication systems are just being established, and obviously all the new kind of communication systems are going to be largely digital in nature. So this picture gives you an idea of the importance of digital communication as a very major futuristic technique of communication for the days to come. Now, why this replacement of analog communication techniques or systems by digital communication systems? There are many advantages. I'll just list out a few of these. First of all, they are believed to be very rugged. What I mean by this is that digital communication systems in general are more immune to noise and channel distortions. Now, the reason why they are more immune is in fact, this also part of the second reason I'm going to give here, and that is because of regeneration along the path. Now, what I mean by regeneration? I believe all of you are at least familiar with the fact that digital communication takes place in the form of let's say ones and zeros, transmission of ones and zeros, transmission of discrete symbols, discrete level of information, right? Information represented somehow in a discrete form. When we learn about pulse code modulation, we'll see how that is done. But let's assume for the time being that it has been done, and that's what we are finally transmitting, ones and zeros. Now, as these signals which contain this information of ones and zeros propagate along any channel, any kind of channel, they undergo some kind of distortion due to the various non-ideal effects that are present in the channel. Also, they collect a lot of thermal and other kinds of noise that is produced along the path and within the communication system. And therefore, by the time the signal comes back to you at the receiver, it comes to the other side, first of all it is very weak because it has propagated over a large distance. Secondly, it has undergone these changes which contain noise and distortion, with the result that the received signal to noise ratio is very poor, and it's very, very difficult to decode the information correctly, right? Now, in a repeater, what you can do is you can at least amplify the signal along the way. You tap the signal somewhere along the way, amplify it and retransmit it. Now, that will not help as far as the noise and distortion are concerned. It will certainly help to increase your received signal power because you are re-amplifying it and retransmitting it along the way, right? But it will not help the signal to noise ratio because the signal and noise and the distortions will all be amplified to the same proportion, to the same extent, right? So it's not going to help you to decode the information correctly very well. So what you have to do is somehow, while you are doing this amplification, also remove some of the noise if possible. Fortunately, that is what is possible in digital communication. At the point of regeneration, at the point of amplification, or what is called regenerative repetition, you not only are able to amplify the signal, but are able to take away the noise that was introduced in that leg of transmission between the let's say between the transmitter and the first repeater, or the ith and the I+1th repeater. Whatever noise was introduced or channel distortion was introduced, you are able to take it away and retransmit a clean signal, right? And therefore, repeated transmissions of clean signals take place. And that is what really brings in the advantage in a digital communication system. You get ultimately noise and distortion not for the entire propagation path, but only for a small segment of the propagation path, which is easy to remove and again clean it up, right? So that is the reason why digital communication systems are primarily having all the major advantages. And now, in addition to this very major advantage, we also have other advantages, and some of them are as follows. They are more flexible. Particularly, they are more flexible from the point of view of hardware implementation. We can use, it's possible to exploit the tremendous amount of technological advancements that have taken place in VLSI when you do digital communication as compared to when you do analog communication, right? It's much more easier to exploit those advantages if you do things digitally rather than if you continue to do them in analog domain. So that is the flexibility aspect. Then when we do digital communication, we can also do all kinds of coding of information, which is just not possible in the analog domain, or at least not easily possible in the analog domain, right? And there are all kinds of coding that one can think of, but one type of coding that is particularly relevant here to talk about is called channel coding. We can do this channel coding to combat or take care of whatever little effect the noise may still produce for you. Whatever little problems the noise may still produce for you can be taken care of through this kind of coding, right? Channel coding. You can also do coding for high fidelity, and you can also do coding for privacy, right? All these things are possible in the digital domain. Well, it's not that these things are entirely impossible in analog domain, but they are much more difficult to achieve and are not as effective as in the digital context. So channel coding can be done, and also coding for, let us say, other uses like privacy. The next advantage is that it is easier and more efficient to multiplex digital signals than it is to multiplex analog signals. Okay, so multiplexing is also easier. I will elaborate on this further when we talk about multiplexing. Finally, in a nutshell, what I like to say is that, see, ultimately what is important is the transmission of information in a correct and reliable manner. And usually the resource that we use to do that is bandwidth. The most important communication resource is bandwidth. The higher the bandwidth you have, the higher the rate at which information can be transmitted on a channel with that high bandwidth. Okay, so after all, when you say we want to transmit information, we need, the basic resource that we need for that is bandwidth. If we want to transmit a lot of information at a very fast rate, we need more bandwidth. That is one aspect. The other aspect is that we need it to be done reliably. And the question that arises is, can one thing be traded off with another? And the usual answer is yes. We can trade bandwidth with performance. We can get better performance provided we are ready to sacrifice or give in more bandwidth. Or in other words, if you have less bandwidth, maybe you will not get as good performance. So this is the cost that you have to typically pay in a communication system. The question then arises is, what are the good ways of trading off? Because one can trade off in a bad way and one can trade off in a good way. You can do this kind of trade-off also in analog communication. For example, you are familiar with AM and FM situation. In analog communication, FM has superior performance compared to noise as compared to AM, but it takes up much more bandwidth to do so, right? So that is also a kind of trade-off between noise performance and bandwidth, which is a major communication resource. The same kind of trade-off is going to take place in digital communication. Now, fortunately for us, it is again, digital communication again scores over analog communication in the sense that this trade-off is more effective, right? You can trade off bandwidth versus noise performance more effectively by using proper techniques. So they are inherently more efficient than analog systems. In SNR bandwidth trade-off. So I believe that these 6 or so reasons that I have given you should be convincing enough about the usefulness of digital communication, and also as to why they are becoming more popular in real life than analog communication systems these days. I think I'll stop our discussion here today with any questions from the floor, because I have not really prepared anything beyond this, not knowing what your background was. So we'll start with PCM and delta modulation next time. But any questions are welcome. As far as the book is concerned, let me make the comment next time. I'll give you more definite. And then, as far as marks distribution is concerned, it's basically a lecture course. So we'll have 2 minors and a major. And if you want, on the Thursday class, we'll have quizzes also. So that will take care of, keep you kind of, maybe most of them, if not all of them. All right, we'll see. That also depends on how efficiently I can correct them and evaluate them. So if we do this kind of a breakup of tests, we can have about 30% for, no, I think 25%. Minor 1, minor 2, 40 for the major, and 10% for our quizzes. Does that sound okay? Does it add up to 100? Oh yes. Any other question?
You're talking about repeaters. That means you are transmitting on cable, aren't you?
No, it could be any kind of communication. If you are doing long distance communication, you require repeaters. You require to regenerate your signal and retransmit it, because the signal is going to become weaker and weaker, and noise is going to get more and more
What I mean is that
difficult.
if you're transmitting on cable,
Yes.
you can retransmit your signal, but the old signal has already been transmitted. So the receiver will receive both signals, isn't it?
Talking of, let's say, radio propagation.
Yeah.
Well, the radio propagation technique. Okay, one thing I like to mention is that we are not talking of the broadcast situation here, right? There are two kinds of communication systems: broadcast systems and point-to-point communication systems. Broadcast systems will continue to be analog for a long time to come, right? We are not really talking about them, where there is one transmitter and many receivers, right? We are here talking about point-to-point communication systems, where you are transmitting from one person or one station to another person or another station located elsewhere. Now, in this situation, usually you have to have some kind of a very fixed kind of link, either cables or microwave or satellites or fiber optic. Okay, so we are really broadly talking about these. Does that answer your question? Anything else? Please feel free to discuss, or although it is a slightly artificial environment, but I think let's try to be as natural as we can be in this.
For broadcasting system, you mean this television and radio transmission.
Right.
They'll continue to remain analog for.
With some digital TV and all that. So that's why I don't want to make a commitment to say yes for all time, but largely I would say yes still.
So to what extent is optical fiber communication being used? Like, let's say you're talking of North American region. How much of this job is being done?
Well, most of the cable systems are being replaced with optical systems, and the reasons are obvious, because you have much more bandwidth and you can transmit much more information, right? But there are limitations still. There are limitations as to the amount of fiber optic cable that you can lay, and the problems that arise which still need to be sorted out, but they are becoming very, very extensive. And I think I won't be wrong in saying that in the next decade optical channels will be the most important channels that will be really in use. Like today it is the satellite and the microwaves and the satellites, but I think it's going to be largely replaced with fiber optic in the next decade.
So what exactly is a microwave channel? Like, what exactly is it supposed to mean, microwave?
Well, I believe you must be knowing about the various frequency bands into which the communication spectrum is divided, and the microwave band is one such band. I mean, you can start from a very low frequency band, go up to the, maybe I can just briefly take a slide on that. I won't be able to give you the exact frequency ranges here because I haven't got them here with me, but I'm sure you can check them up in your textbooks. You can start with as low as what is called the VLF band, very low frequency band, and then come up to the HF band. I'll say VLF and low frequencies, then the high frequency band, then the VHF band, then the UHF band, which is also the lower end of the microwave band, right? UHF, microwave, they merge with. Then we have the higher frequency bands. So microwave starts somewhere from here and goes up to about a few gigahertz. The exact frequency ranges you can check up in your book. They're all there. Now, so when you do communication in this frequency band, the microwave band, we say it's microwave communication, right? The propagation modes that are used in different bands are different. For example, UHF and microwave use what is called skywave propagation. You familiar with that? Skywave or line of sight propagation, right?
Up to the point goes straight and
That's right.
without
There is a direct path between the transmitting antenna and the receiving antenna, right? That's why, and obviously because this path has to be direct, they are limited by the over the horizon distance. I mean, you can't go beyond the horizon. So if you want to increase the distance of propagation, you have to increase the height of your transmitting and receiving antennas. That's why you will find microwave towers to be pretty high, so that they can space them out as far as feasible. Okay. If you are working with the VHF band or the HF band, particularly in the HF band, you are using the ionospheric propagation. That is, the transmitting antenna actually reflects slightly upwards, and then the ionospheric layer in the upper atmosphere reflects these radio waves back towards the earth. Actually, it bends it back towards the earth, and this way long distance communication is rendered possible, because you can communicate. Suppose this is your earth, that's your ionosphere. You may transmit from here, and you may be able to receive here beyond the horizon. So you'll find a lot of broadcast being done in the HF, for example. A lot of other kind of communication, point-to-point communication, also being done in HF, right? And of course, there are other similar considerations in VLF and VHF. I thought you were familiar with these things, so I didn't take that up, because that's typically done in the first course in communication.
So why can't FM be broadcast over long distance? Like,
Same reason, because you are using a band of frequencies which propagate in that particular, because you need a higher bandwidth in FM. If you need a higher bandwidth, you need a higher carrier frequency, and that carrier frequency will be in the VHF or the UHF band, and therefore you are limited to the skywave propagation mode. Okay, so it's an indirect reason. Any other questions?